All right, so we're going to do sections 4.2 and 4.3 together. 4.3 will be the last part of this section, last part of this lecture. The reason we're putting them together is because they actually fit together really well. They're about the same thing, same topic, and 4.3 is just a small extension of the ideas from 4.2. All right, so this section is about solving equations involving trig functions, And again, as usual, we're going to focus on sines, cosines, and tangents. Mostly on sines and cosines, because they're the ones where there's the most complications. All right, so what do we mean by this? Let's start just with an example. Find all, so here's the important word, x, so that sine x is equal to 1/2. All right, so problems in this section a lot of them will look like this. Find all the x so that when you put that number into sine, right, as an input, you'll get the output 1/2. Okay, so this is different from the last section, 4.1, which was the inverse function section, where there we often had to do the same idea, right? In the last section, if I was asked what's arc sine of 1/2, right, equals question mark, the way kind of we presented it was this is the same as asking sine of what is equal to 1/2, right? And then we said, well, the what, we've memorized it, it's pi over 6. And so arc sine 1/2 is equal to pi over 6. And then we were done, all right? However, that's not what we want today, or not what we want in this section. In this section, I want all the x, right? So for the arc sine problem, there's only one output, right? Because when you put in one input into a function, you should only get one output. So it was just the answer pi over 6. Here, x equals pi over 6 is an answer, but it's not all of them. There's many, many others. And that's because sine is a periodic function and it repeats quite a lot, right? It repeats like that. And so what happens is when I look at the output 1/2, that's represented by drawing a horizontal line at height 1/2. Okay, and every intersection point of this horizontal line with my graph, that's going to be a solution to my problem, right? It's going to be a value that when I plug it into sine, I get the output 1/2. So we can immediately see that this kind of problem in 4.2 will have infinite number of solutions. All right, if it has solutions. But this one does. So the question is, what are all those solutions, right? And how do we write them down? Okay, so it's really important to kind of differentiate the idea between finding the arc sine and solving the problems from this section. All right, so this section we're again looking for all the solutions. All right, so the way I'm going to present this is going to be very different from the book. I hate how the way the book does it, because their way of doing it relies very heavily on memorization. And if you look at their kind of description of what the solution is, there's a whole bunch of cases. If, x is this or that, if the right-hand side of the equation, this 1/2 bit, is this or that, then you have to remember it to do it like this. If the right-hand side is 0, then you have to remember that. If the right-hand side is 1, then you have to remember this. So I hate it because not just for sine, it's going to be the case for cosine as well. So you end up having to memorize a whole bunch of things. And it's, again, as usual, it's really, really easy to memorize something incorrectly. And if you don't really understand what you're doing, you'll never catch your mistakes, and then you're going to be in big trouble. So the way I'm going to present it is one that depends on reasoning. reasoning out what all the answers are going to be through the graph. So this is why I so heavily emphasized knowing the graphs of our trig functions from the beginning. So let's look at the graph of sine. The graph of sine looks like this. All right. Let me mark a few important points. 0 to 2 pi. This one here is pi. For this, I'm not going to need any more. All right, for this particular problem. So I'm looking at, again, I want to solve sine of x is equal to 1/2. And the first step is kind of the same as before, where we find one solution, all right? And we've already said x equals pi over 6 is one solution, right? And again, the question is, what are all the others? What are all the others? Okay, so that's the question I'm going to answer with the graph. So the idea is I'm going to look at the graph. I'm going to say pi over 6 lives, pi over 6 is less than pi over 2, right? In degrees, pi over 6 is 30 degrees. Pi over 2 is 90 degrees, right? So I guess I should have labeled an extra point here. Here's pi over 2, right? So pi over 6 lives between 0 and pi over 2. I don't care exactly where. Let me put it right there. Okay, so let's say that's pi over 6. All right, so one thing that we can notice from the graph is if this is pi over 6 here, right, we know pi over 6 is 1/2. So when I go up, that height right there is 1/2, right? That's the meaning of sine of pi over 6 is equal to 1/2, right? Okay, now, if I do this kind of horizontal line here at the height 1/2, right, all the way to 2 pi, I can see that there's another point right here. So this is the one that we just found, right? Sine of pi over 6. So let me write down this. This point, this red point right there represents the fact that sine of pi over 6 is equal to 1/2. Okay, so this point right there, that second one that I've drawn, represents the fact that sine of that angle equals 1/2, right? So that's going to be another solution to the problem. And again, what I'm looking for are what are all the solutions, right? What are all the others here? So that's another one. So I want to figure out exactly where that guy is. So I'm going to reason it out like this. And we did this in the last lecture, but here it's very critical to think of it this way. So here I noticed that this distance is pi over 6, right? That's pi over 6. Let me do it down here, right? So this is pi over 6. Why is it pi over 6? Well, that's literally what this point being pi over 6 means, right? That its distance to 0 is pi over 6. Now, this hump right here of sine is symmetric to the other hump, right, on the other side of pi over 2. All right? So if this height from here to here is 1/2, then this height also is 1/2 when this distance is pi over 6. Okay? Because of the symmetry, right? If I move from here to here, that's a distance of pi over 6. So when I move from here to here, the same distance, then this height should be the same as that height. All right? So this is the critical kind of reasoning that we need for this section. Okay? All right. So what exactly is this? What point is this? Well, it's a distance of pi over 6 from the position pi, right? Because this point right there is pi. So it's to the left of pi. So the exact coordinates of that point are going to be, so the exact coordinate of that point is going to be pi minus pi over 6, right? Again, this point right there is pi. I'm moving to the left by pi over 6, so that would be pi minus pi over 6, which is 5 pi over 6. Okay, so my second solution that I found is 5 pi over 6. So x equals 5 pi over 6 is another solution. All right. Okay, now I'm only going to look, so notice I've only looked between 0 and pi, right? When I drew this horizontal line, I only cared about the region, the region between 0 and pi. That's because if I find what happens with sine between 0 and pi, then because sine is periodic, because it repeats every 2 pi, sorry, did I say 0 and pi? Because sine, if I figure out what's going on between 0 and 2 pi, then because sine is periodic, it repeats every 2 pi, then automatically I get all the other solutions because they're always every 2 pi away from the previous one. All right. So between 0 and 2 pi, I've got two answers, right? Oh, let me fill this in here. Sine of 5 pi over 6 is also 1/2. Okay. Now, if I were to extend this horizontal line, I would get another solution right there and another solution right there. And if I extended it to the left, I would get another solution right there, right? And then another solution right there, and so on, right? Every time there's a hump, I'm going to get two solutions, all right? But I don't have to try to figure out where those other humps are because I know that from the very first hump that I found, from the very first solution that I found right there, if I move a distance of 2 pi, I'm going to get to that guy, all right? From this one that I just found, the second one that I found, if I move a distance of 2 pi, I'm going to get to that one. All right. So if I wanted two more solutions, it would be this one right here would be at pi over 6 plus 2 pi. Right. So let me indicate that here. This one is pi over, let me write this as kind of in the same way as I wrote the other. So this is sine pi over 6 plus 2 pi equals 1/2, right? That's what the meaning of that red point. The meaning of this one is sine of 5 pi over 6 plus 2 pi equals 1/2, all right? So every 2 pi, I'm going to get another two solutions. And to the left, the same thing works. If I move 2 pi to the left, so this guy here is going to end up there, all right? So this one is going to be sine of pi over 6 minus 2 pi equals 1/2, all right? And then this one right here is going to be sine of pi over 6, 5 pi over 6, my second one, minus 2 pi is equal to 1/2, all right? So that would be going this way, okay? So I can figure out, I automatically have all the solutions once I've found, I have all the solutions, period, once I've found all the solutions between 0 and 2 pi, okay? So let me write over here, all other solutions are can be written in terms of these two. All right, and the way we're going to write it is x equals pi over 6 plus, and then if I add 2 pi, I get to another one, right? But if I add another 2 pi, so in other words, I add 4 pi, I get to yet another one. That would be, if I add 4 pi, that would be the one over here. All right, so, and if I add 6 pi, I'll get another one, and so on. So any number times pi, I'll get another one. Any whole number times pi, I'll get another one. Times 2 pi, sorry. Any whole number times 2 pi, I'll get another one. Including negative numbers, right? Just like we said over here, this would be minus 1 times 2 pi. So the way I'm going to write it is plus 2 pi and then times any whole number, k. So whole numbers in math, we usually call them integers. So this is an integer. Okay, so k is equal to any, let me write it as one sentence here. K can be equal to any integer. All right, so in other words, k equals 1, 2, 3, and also ... minus 1, minus 2, minus 3, ... All right, so that gives me all the solutions that, or this is a way to write down or to express all the solutions that come from the first solution. All right, so if, in other words, if I wanted you to tell me another solution, then you could use k equals 1 So that would be pi over 6 plus 2 pi, whatever that turns out to be, right? 13 pi over 6. If I want you to give me another one, you could use pi over 6 plus 2 pi times 2. So pi over 6 plus 4 pi. Another one, pi over 6 plus 2 pi times 3. So pi over 6 plus 6 pi. Or pi over 6 minus 2 pi, pi over 6 minus 4 pi, pi over 6 minus 6 pi, and so on. All right. So this is a shorthand for writing an infinite number of solutions. Okay. From the other set, x equals 5 pi over 6, I also have 5 pi over 6 and then plus 2 pi k, right? The same every 2 pi, you get another solution. Okay, so altogether, my solutions are going to be things that look like this and things that look like that. All right, so the way we're going to write it in this section is like this. So x such that, so the way we read this vertical line here is such that. Okay, so x such that x is equal to pi over 6 plus 2 pi k. All right, and then our book likes to use the word or here. So we could use or just a comma. I think maybe let's just use a comma. X equals 5 pi over 6 plus 2 pi k. And then close parentheses. And then probably you should say k equals any, k equals any integer. Okay, so this is a nice shorthand way of expressing every single solution to the problem. All right. Okay, so it looks like this is a little complicated, but ultimately you just need one solution. You look at the graph. The graph will tell you where the other solutions are between 0 and 2 pi. And then once you know all the solutions between 0 and 2 pi, you can kind of replicate them using this 2 pi k idea here. All right. Okay, let me do a few more examples, and then we'll kind of see through these examples why the book's method of kind of going through this formula, memorizing this algorithm or formula is not so great. Okay, but first let's do one like this. Let's solve sine of x equals minus root 3 over 2. Okay. All right, again, I want, when I say this, I want every single solution, not just one, right? So here, sine of x equals minus root 3 over 2. There's a few ways to reason this one out, but let's do it from the graph, right? Because, again, just to emphasize how important the graph is, or knowing the graph is. Okay, sine of x equals minus 3 pi over 2. I know that sine, so let's forget about the minus sign for a second, right? I know for a fact that sine of pi over 3 is equal to 3 pi over 2, right? That's one of the ones that we've memorized. 3 pi over 2 equals root 3 over 2. That's one of the ones I've memorized. So let's plot that. So pi over 3 is less than pi over 2 again. So here's pi over 2. Let me label some of these. This is pi. This is 3 pi over 2. And this is 2 pi. And remember, I only really need up to between 0 and 2 pi because I'm going to replicate the rest using the 2 pi k. Okay, pi over 3 lives somewhere like here. All right, and again, this doesn't have to be, have to be perfectly accurate. But I'm really interested in on which hump pi over 3 is, and it's the first hump. Okay, pi over 3 is there, and so this height here is root 3 over 2. Okay, all right, that's not what we want, right? We want minus root 3 over 2. We want our output, we want to find a point so that we get the output of minus root 3 over 2, right? So again, we're going to use the symmetry idea. This hump right here, which represents the first quadrant, if you want to think of it that way, is the same as this hump right there, right? And so except this hump down here is upside down, right? And so this distance right there, right here, from here to there is pi over 3. If I move a distance from here to there, a pi over 3, then I get to a height of, then my output's going to be a height of root 3 over 2. So because of the symmetry, that means if I move from here to here, right, where this distance is pi over 3, then this height here is going to be exactly minus root 3 over 2. All right. Okay. So if we think about it that way, we have we have one solution, because this point right there is a solution to our problem, right? What is that point? It's pi and then another pi over 3 to the right. All right. So that point right there is at position pi plus pi over 3, which is 4 pi over 3. Okay. And so this reasoning tells me that sine of 4 pi over 3 is equal to minus root 3 over 2. Right? Again, it's minus. We're on the negative hump here. All right. So so I have one solution, right? So x equals 4 pi over 3 is going to be one solution. Now, if I look at this horizontal line again at root 3 over 2, I can see that it hits my graph of sine at two positions. Right there, we've already found this one, and right there, right? So my next goal is to figure out where that guy is. And here again, we can use symmetry. This hump right there is the same as our initial hump between 0 and pi over 2, except it's upside down again. This little part from 0 to pi over 3 is equivalent to this part from 2 pi, except going to the left, pi over 3. All right. So if I move to the left pi over 3 from 2 pi, right, it's the same as moving, or in terms of kind of the humps, in terms of the hump structure, it's the same as moving right pi over 3 from 0. Okay, so what that means for us is that this height right there is exactly the height that we want. Okay, so what is the position of that point right there? We're moving left by pi over 3 from 2 pi. So it's going to be 2 pi minus pi over 3. All right, and that's going to be 6 minus 1, so that's 5 pi over 3. Okay, so our second solution is going to be at 5 pi over 3. All right. Okay, so this kind of reasoning tells me that I can get all the other solutions by replicating these two guys, right? Plus 2 pi k. So this would be replicating, if I continue this picture here, it would be getting this 4 pi over 3 plus pi k, 2 pi would be this one. All right. And then if I do plus 4 pi, that would be another one, the next hump, and so on. All right. And then, of course, plus 2 pi k here gives me, well, plus 2 pi gives me that one, and so on. All right. And when k is negative, I get the humps on this left side here. Okay. And so these are going to be my solutions. And again, I write it as x such that x equals 4 pi over 3 plus 2 pi k, comma, x equals 5 pi over 3 plus 2 pi k. And a k is equal to any integer. All right. Okay, so again, very straightforward. If you're very comfortable with the graph, and if you're comfortable doing this kind of symmetry argument. All right. Okay, let me do another point of view for the same problem. So the way I chose to do this problem just now was I looked at the hump, I looked at sine from 0 to 2 pi, and I found all the solutions. But alternatively, you could look at any kind of period of sine, any interval of size 2 pi. So I could actually do this problem also by looking between 0 and pi. So that would be pi here. And then from here, 0 to minus pi. All right. So this might be, so I think a lot of people maybe aren't as comfortable with this because we see the graph of sine from 0 to 2 pi a lot, right? So we're very used to it. However, anytime you kind of cover an entire period, right here, minus pi to pi is 2 pi, right, a distance. So this is an entire period of sine. And so we could use this to do the same problem. And this one is a little nice because it's symmetric about the origin in a way, except upside down, right? And so I knew this point here, the point I wanted was pi over 3, right? Or not the point I wanted, but I knew that sine of pi over 3 was root 3 over 2. I wanted minus root 3 over 2. And so what happens is if I look on the opposite side, that's going to be exactly negative of it, right? So if this height here is root 3 over 2, then this height here is minus root 3 over 2, right? And what is that position? That's going to be minus pi over 3. And essentially, in kind of maybe simpler words, all I've expressed was the fact that sine is an odd function, right? So sine of minus pi over 3 is minus root 3 over 2. And so this way, I kind of get an easier expression for my first solution, right? X equals minus pi over 3. Okay, so it was maybe a little easier than figuring out the 4 pi over 3 that we did just now. Okay, so for the second solution, right? So we can see again, I'm working between minus pi and pi. So if I draw a horizontal line at minus root 3 over 2, I can see another solution right there, right? And so I would need to figure that guy out. Okay, so what is that one? Well, I can use another, the same type of argument. Going from here to there, that's a distance of pi over 3. And so going from here to there should be a distance of pi over 3 as well. And again, this depends on the fact that this hump is symmetric to that hump. All right. And so this distance, sorry, let me do this in red here. This is this distance is pi over 3. That distance is pi over 3. And so we're moving to the right pi over 3 from negative pi, right? And so what that means is the position of that point right there is minus pi plus pi over 3 because we're moving to the right. And so ultimately this is going to be minus 2 pi over 3. All right. And so my second solution is going to be x equals minus 2 pi over 3. All right. And then now we can, again, we can duplicate or replicate these solutions by shifting by 2 pi, right? Plus 2 pi k plus 2 pi k. And that gives me all the other solutions, right? And so if I did it this way, I would express my solution like this. X equals minus pi over 3 plus 2 pi k. X equals minus 2 pi over 3 plus 2 pi k. And again, k equals any integer. All right, so you could do this either way. Our solutions look different, but they're actually the same. In that, if I look at, let's say the first way I did it up here, if I look at k equals minus 1, right? If k equals minus 1, that corresponds to 4 pi over 3 minus 2 pi, which is 4 pi over 3 minus 6 pi over 3, which is minus 2 pi over 3, right? And so that one actually corresponds exactly to this guy right here with k equals 0, right? So every solution up in the first way I did it corresponds to some solution down here with a different k. Okay, so all I've done is I've expressed the solutions in a different way, but ultimately I've covered all the different solutions. So whichever way you want to do this, whichever way you're more comfortable with is fine because they're both express the same solutions. Okay, in general, I've found that perhaps people are more comfortable just always thinking from 0 to 2 pi. But, whatever you're comfortable with is fine. Okay, so let's do another example. What about solve sine of x is equal to 1, right? So this is where kind of my method, I like my method more than what the book does, because the book basically if you look at the way they do it, the book has a algorithm or kind of like instructions that say, if you're looking at sine of x equals 1, then the solution is this or that, right? So you have to memorize kind of a separate situation. But for my method, you just look at the graph. Here's the graph, right? We know already that sine of pi over 2 is 1. All right? Or we also know that from the graph, just looking at the graph, right? That maximum height right there is at pi over 2. Okay? Now, where are all the other solutions? So this is different from the other problem, other problems that we did, because if I draw this horizontal line, it only touches at one place, at pi over 2, right? And so there is no second solution to find in this situation. So that's it, pi over 2, and then I propagate the pi over 2, right? Because again, if I continue the humps, I'm going to get another solution right there. But that solution is just the one that I just found plus 2 pi, right? And if I keep on kind of drawing sine, I'm going to have another one here, but that's just this one plus 4 pi, right? If I draw on the left, I'm going to get one here, right? That one is the one I found, minus 2 pi. And then there'll be another one, minus 4 pi, and so on. Okay, so just looking at the picture, I know there's only one solution, and then I propagate that one, or I replicate that one. Okay, so my solutions is going to be x. So I guess let me write it as the way it kind of I've been writing it. So x equals pi over 2, and then plus 2 pi k, and then note no others. Right? And again, the way, if you kind of just memorize the book's procedure, you just have to memorize, for this situation, there are no others. But if you look at the graph, you easily see that there are no others. Okay? And my solution, kind of written the book's way, is pi over 2. Well, not just the book's way, but this is very, very standard. Pi over 2 plus 2 pi k. And that's it. And then k equals any integer. All right. And again, the way we read this is my solutions are any x such that x takes this form here. All right. Okay, so again, I think this is often a little bit abstract. So just to emphasize that this is just shorthand, let me write down a few solutions, right? So pi over 2, that corresponds to k equals 0, right? Pi over 2 plus 2 pi, which is 5 pi over 2, that corresponds to k equals 1, right? Pi over 2 plus 2 times 2 pi, 4 pi, that corresponds to k equals 2, right? So that's going to be 9 pi over 2. And on the other side, pi over 2 minus 2 pi, that's going to be minus 3 pi over 2, right? That corresponds to k equals minus 1, and so on, right? Every k will give me a new solution to my problem. And there's an infinite number of k's, so there's an infinite number of solutions. All right. Okay. So a lot of the, if kind of the generic problem will be more like the two examples that I did above. But there are some other ones which are kind of special cases, like the one we just saw, right? So if I want to solve sine of x equals 0, right? That one's also a special case because sine looks like this. And the two solutions between 0 and 2 pi are going to be at 0 and at pi, right? So x equals 0, x equals pi. And then again, plus 2 pi k, plus 2 pi k. All right. But let's think about this one. 0 plus 2 pi k is just 2 pi k, right? Pi plus 2 pi k is equal to 3, sorry, not 3. Let me write it like this. Let me pull out the pi. So this is 1 plus 2k times pi. All right. So if you think about this a little bit, these guys are all going to be the even ones. These guys are going to be odd, right? 1 plus 2 times something is always odd. All right. So what's going on here is the first set of solutions are going to be all the ones which are actually even. So this is x equals 0, 2 pi. Let me extend this picture. This is 2 pi. And then if I add another 2 pi, I get to 4 pi. If I add another 2 pi, I get to 6 pi, and so on, right? Whereas this one is at pi. If I add 2 pi, I get to 3 pi. If I add another pi, I get to 5 pi. So this second set of solution represents actually all the odd times a pi. The first one represents the even times a pi. So altogether, we get everything times a pi, right? So for this one, the solution is actually equal to pi k, right? Where k is equal to any integer, right? Because it's any number times pi, right? Pi, 2 pi, 3 pi, 4 pi, minus 2 pi, and so on. All right, so this is a kind of a special case, and we can write it like this: x equals pi k. K equals any integer. So this one, it takes maybe a little bit of reasoning, but ultimately, if you just look at the graph also, it makes complete sense, right? Because you can see that it hits 0 at every number times pi, minus 1 times pi, minus 2 pi, minus 2 times pi, minus 3 pi, and so on. Okay, and then finally, one for you to play with is solve sine of x equals -1. And that's another kind of atypical situation because in the regular period, there's only one solution. So it's very much like the sine of x equals 1 situation. All right, but that's the core idea behind this kind of problem. So next, I'm going to do cosine. I'll just do a couple examples for cosine because the idea is exactly the same, but of course the humps are going to be different because it's going to be the humps of cosine instead of the humps of sine. So let's do cosine. So solve cosine x equals √3/2. All right. Okay, so let's draw our cosine between 0 and 2 pi. All right. Let me mark this one as pi. That one is pi over 2. That one is 3 pi over 2. Okay. Cosine x equals √3/2. I already know, I've already memorized, x equals pi over 6 is a solution. Right? So I plot that. So again, I'm literally doing the same things. I plot that right here, pi over 6, right? And so of course, you know, what that means is this distance here is pi over 6. Okay. Now I look at this picture. Let me go up to here. This is going to be √3/2, right? Height of √3/2. And if I draw a horizontal line, I see that I'm going to get another solution on this side right there. Okay. All right. Where is that guy? Right. So first of all, those are the only two. So once I found these two, I can propagate or replicate to get all the others, right? Again, same idea. I only have to look between 0 and 2 pi. So where is this guy? Well, this hump here is symmetric to that hump, right? Except they're kind of flipped, mirror flipped, right? And so this distance here of pi over 6 from 0 to pi over 6 is the same as this distance here from 2 pi to the left a distance of pi over 6. Okay, so this distance here should be pi over 6. And if it is pi over 6, that gives us exactly the position that we're looking for. All right, so now it's to the left of 2 pi. Let me make that 2 pi a little smaller. And this 3 pi over 2 a little smaller. It's to the left of 2 pi, left by amount of pi over 6. So that means this position is 2 pi minus pi over 6, which is 11 pi over 6. All right. And so my second solution is x equals 11 pi over 6 is another one, another one. And so all of them are x equals pi over 6 plus 2 pi k. 11 pi over 6 plus 2 pi k. K equals integer. These are all of them. All right. So all solutions. And so again, in our notation, x such that x equals pi over 6 plus 2 pi k, x equals 11 pi over 6 plus 2 pi k, k equals any integer. All right. That's too messy. So k equals any integer. Oh, okay. All right, so again, pretty much exactly the same idea, except the picture is different. So our symmetries are a little different. Okay, so that said, just like with sine, we can approach this in a slightly different way. We can look at cosine, right? We know cosine looks like that. And so once we found this pi over 6 solution right here, that was right there, we know that on the opposite side, minus pi over 6, we're going to have the exact same solution because cosine is even, right? So we could have also said x equals pi over 6 and x equals minus pi over 6 will give me 2 of them, right? How do I know this will cover them all? Well, here I have to draw all the way up to 2 pi, and I have to recognize that this one plus 2 pi will give me that one there. All right. And so I am finding all of them that I need, right? And in fact, notice that this actually works, right? Minus pi over 6 plus 2 pi is exactly the computation we did before, 11 pi over 6, right? So that's actually exactly the one that we just found, all right? So an alternate way to write this solution is x such that x equals pi over 6 plus 2 pi k, x equals minus pi over 6 plus 2 pi k, k equals any integer. All right. So whichever one you're comfortable with is fine. But again, I found that a lot of people are more comfortable working always kind of consistently working between 0 and 2 pi. Okay, let me do one more kind of half example for cosine. What if I need to solve cosine of x equals let's say minus root 2 over 2, right? Then I know that cosine of root 2 over 2, cosine of pi over 4 is root 2 over 2, right? And I know that this hump here is symmetric to that hump there, right? So this point here is pi, pi over 2. And this point here is pi. And so I know that because this distance is pi over 4, right, then therefore I need to look at this distance here, pi over 4. Okay, because I'm looking, one way to think about this is I'm looking at the hump, which is I'm thinking of it kind of in a direction from the top of the hump going down to the bottom, right? Going down towards 0, let's say it like that. And if I think about it like that, I'm moving from here towards there, a distance of pi over 4. Okay, So if I do the same thing kind of on this side, this top of the hump up here is symmetric to that hump right there, that point right there. And then I'm moving again towards the ground like that. All right, that was a little crooked. I'm moving towards the ground like that. All right, so since I'm moving this way, I need to start from here and move that way a distance of pi over 4. Okay, so again, think of this as a mirror, as kind of like a mirror image. You have a mirror right there, right? And so if I'm traveling from here to there, that would be like traveling from here to there. Okay, so that's how I know it should be pi minus pi over 4. All right, so the point I'm looking for is pi minus pi over 4, which is 3 pi over 4. Okay, so that finds me my actual first solution to my problem. And then I need to use symmetry to find that one, right? And for that one, I would think about the hump as going from here to there, going that way. And so I would want to do going that way like that. And so for that one, I would need to start at pi and move to the right by pi over 4 to get to the correct position. Okay, if I move right a pi over 4 from pi, I would end up at pi plus pi over 4. That would be 5 pi over 4. Okay, so those would be my two core solutions. And then I replicate, and then I replicate. So plus 2 pi k, oops, plus 2 pi k, and that gives me all my solutions. All right. Okay, and again, just as with sine, there's exceptions to this kind of always having two solutions. So the two examples we just did, they have two solutions for each of them, and you replicate them. But of course, there's exceptions because cosine, let's say between 0 and 2 pi, looks like that. So if I wanted to solve cosine x equals minus 1, there's actually only one solution from 0 to 2 pi. All right, so my solution would be similar to the one for sine of x equals 1. All right. Okay. Also, if I were to ask what's solve cosine of x equals to 1, then you would have this one here, and then you replicate that to get to there, replicate to get to there, right? So there is for sure kind of exceptions. So last one, cosine x equals 0 would be this one. And then you have to figure out where that one is using the symmetry again. Well, you don't have to use symmetry because hopefully by now we're comfortable knowing that this is pi over 2 and that's 3 pi over 2, right? And then you replicate and you replicate, all right? Okay, so those are the cosine problems. Finally, tangent. And after all this work, luckily for us, tangent is easy. Let's say I want to solve tangent x equals 1. This one's easy. Tangent x is easy because tangent doesn't have all these humps, right? Tangent looks like this. Between 0 and, between minus pi over 2 and pi over 2, minus pi over 2, pi over 2, right? There's only ever one solution, right? So tangent x equals 1, I know that sine and cosine are the same at pi over 4. They're both root 2 over 2. So tangent of pi over 4 is equal to 1. All right, so pi over 4 lives there. All right, and as you notice, right, for the graph of tangent, again, there isn't kind of multiple humps between in the period, right, between minus pi over 2 and pi over 2. So there's only exactly one solution. And so now I just replicate this one solution, right? There is no other solution within the period. And all the other solutions are just, I shift by a period amount, right? Here to there. And then here's another one, here to there. That would be subtracting. And then I could get another one over here, and so on. Okay, what's the period of tangent? The period of tangent is pi. So all of them are going to be pi over 4 plus pi k instead of 2 pi k, right? Because, again, we're shifting a distance of pi every time for tangent because the period is pi. All right. Okay, so tangent problems are a little bit more straightforward than the sine or cosine ones. All right, finally, for the end of 4.2, you'll see some problems that are kind of the same problems as the ones we just talked about, but slightly hidden. So for example, solve 2 cosine x equals -1, right? So how would you solve this? You transform it into a problem that we just learned how to do. So this is the same as cosine x equals -1/2, right? And that's the type of problem we just learned. Solve cosine of x equals some number, right? Or solve sine of x equals some number. Okay, so convert it to a problem that we just learned how to do. So another one, solve 2 cosine x plus 1 equals 0, right? This doesn't look like, anything familiar, but if we rewrite it as 2 cosine x equals -1, and that's the same as cosine x equals -1/2, that's the kind of problem that we just learned, right? Find cosine x equals some number. Okay, so these two are kind of these two problems here are kind of secretly the ones we just learned. Okay, and of course the same with sine. So maybe I have solve 4 sine x plus 2 root 3 equals 0, right? Again, it looks really nasty. We have, all sorts of things, looking to be added to each other and stuff like that. But if we write it in terms of a problem we know how to do, this is 4 sine x equals -2 root 3, which is sine x equals -2 root 3 over 4, which is minus, sorry, let me write it on another line, which is sine of x equals minus root 3 over 2. And again, this is exactly what we've just learned. Sine of x equals a number. All right, so we just used a procedure that, that we just learned. So in 4.2, these will be the kind of more difficult looking problems. So in 4.3, we're going to complicate matters by having something that's more complicated than just x inside here. All right. So what makes these three that I just drew or that I wrote down, these three are kind of easy because this thing is happening outside the sine. This thing is happening outside the sine. Notice here, outside the cosine, outside the cosine. And here, outside the cosine, outside the cosine. So that makes it so that I can easily rewrite it as the type of problem we just been talking about. But 4.3 is where the stuff is on the inside of the sine, and then we cannot do something as simple as that. All right, before I get into 4.3, let me mention one thing. So if you see a problem like this, solve cosine x, let's say 2 cosine x equals 3. Sorry. That's equivalent to cosine x equals 3 over 2. And then what's the solutions to this? Well, here's the graph of cosine. There's 1. There's -1, right? Cosine never goes above 1. It never goes below -1. So cosine x is never 3 over 2. So no solutions. All right. All right, so just be aware of that, right? So obviously cosine, you can never have an output of cosine or sine that are bigger than 1 or less than -1. Tangent is fine though, remember. You can have tangent of x equals 5 halves. That's perfectly legal. All right, originally I was thinking of doing both 4.2 and 4.3 in this one video, but it looks like this video has been pretty long. So I'm going to do 4.3 in a separate video.